between Wei Li and Jim. Not Tom.
Okay, so our first speaker today is Wei Li. She will talk about sparse resultants in differential and difference algebra.
Okay, thanks. So before the talk, I would like to take the opportunity to thank the organizers who invited me to speak here. And today I'm going to talk about the theory of sparse resultants in the ordinary differential and the difference algebra. So this is joint work with Xiaoshan and Chunming. So let me propose the main problem we are considering. Suppose we are given a system of n+1 equations in n variables. This overdetermined system might be algebraic equations or differential polynomial equations or difference polynomial equations. And we want to find conditions on the coefficients of these polynomials such that the vanishing of these algebraic conditions gives a necessary and sufficient condition that this system has a solution. So here, for the if and only if condition we are speaking, it is in the sense of the Zariski closure or Cousin closure or coin closure, depending on which context we are talking about.
So what do you mean by closure?
I will say it later.
Okay.
I will explain.
What is in the sense of Zariski closure? What data there are in the sense of Zariski closure?
Polynomial or differential?
Is in the sense?
What is in this?
What on the sense?
What on that slide do you mean in the sense of Zariski closure?
This if and only if condition.
No, but
Is R?
It is not the exact if and only if condition, but
what do you mean in the sense of Zariski closure? What do you mean? I don't know what it.
I think what was meant is that this if and don't leave holds on the Zariski dense set of parameters.
Yeah, it means.
Yes, that's what I'm asking. What it means. I'm asking what you mean by this. I'm asking what you mean by in the sense of Zariski closure.
Yeah.
Almost.
So this is for the sufficient condition. So that means in a Zariski dense set of this in a Zariski closure, but in a Zariski dense set of this variety, the system will have a solution, not of the whole.
Okay, thanks.
Yeah, I will explain it later.
Okay, sorry.
Okay, so if these algebraic conditions exist, we call it the resultant or the resultant system. And the main problem here is to show whether such resultant exists. If it exists, to explore its basic properties and devise efficient algorithms to compute the resultant.
And R is supposed to be purely R is algebraic or differential algebraic, or what is R?
So here, the resultant, I'm talking both the algebra case, differential case, and the difference case.
So differential case, it'll be differential polynomial.
Differential case were differential polynomials, like these algebraic differential or difference equations. So for the here's the outline. So for the motivation, I will first introduce the algebraic sparse resultants, and then we move on to the main parts, the sparse differential resultants and the sparse difference resultants. At last, we conclude the talk and propose some unsolved problems. So the simplest resultant is the Sylvester resultant for two univariate polynomials. So given f and g, there are two polynomials in a variable x. So the Sylvester resultant of f and g is the determinant of this matrix. And it's well known that the vanishing of the Sylvester resultant gives a necessary and sufficient condition that f and g has a common root. And this is for univariate case, and for n+1 polynomial
Wait,
Oh, sorry.
when you say common root, do you include infinity?
That's what I was going to ask.
What?
Do you include roots at infinity?
No,
Because-
this is just a fine case.
But
And,
then you should
yeah, we-
include
we-
inequalities, right? In equations for BM and AL.
Yeah, they have at least one non-zero.
Yeah. So okay.
Yeah.
So there's this even leave up to this assumption.
Yeah, yeah,
Okay. Mhm.
yeah. And for n plus 1 polynomials in n variables, the multivariate resultant is also known as Macaulay resultant, because Macaulay was first to give the rigorous definition and give the determinant forms to compute the multivariate resultant. Okay, and for algebraic sparse system, so the resultant are one of the main elimination tools in elimination theory, and it can be used in the polynomial solving problems or the implicitization problems. Sometimes we need to eliminate some of the variables, so we want to get a non-zero element. So in some cases, when the system is very sparse, the Macaulay resultant might be identical or zero, so it cannot provide useful information. So we need to consider the sparse, the construction of the sparse system. So for algebraic sparse polynomial systems, the number of isolated roots in C star n. Here, C star is the non-zero elements in the complex field. So the number of isolated roots is bounded by the mixed volume of the Newton polytopes of the Fi. This is also known as BKK number. So usually it is smaller than the below bound. So this simple example illustrates it. So given f1 and f2, there are two polynomials in x1 and x2. The below bound is 2n squared, and the BKK number is 2n. So the BKK number is smaller than the below bound. It gives a better degree bound. And the algebraic sparse resultant is closely related to the BKK number. It was first introduced by Gelfand in 1991 when studying the hypergeometric forms. And these term fields give the general definition for the sparse resultant and proved its basic properties, such as the system has common solutions in C star n, we call it non-zero solutions. If and only if the sparse resultant equal to 0 here, it is also in the sense of Zariski closure. And the degree of the sparse resultant in the coefficients of each polynomial is equal to the mixed volume of the other n polynomials. Has BKK degree bound. And Kenny and Miris introduced the metric formulas for sparse resultant and give efficient algorithms to compute the sparse resultant based on the subdivision method. And then D'Andrea proved that the sparse resultant is equal to the quotient of the two determinants. So like the Macaulay resultant, it has the determinantal representation forms for the sparse resultant. So here, this is basic things for the algebraic sparse resultant. Okay, let's move on to the differential case. So here, always assume E is a fixed universal differential field over a base differential field. The base differential field might be the rational number field or the rational function field or some other differential field we are considering the coefficient field. And the EY, we use EY to denote a subset of E consisting of all the elements whose derivatives are not zero up to any order. And we sometimes call it a non-polynomial element. So as in the algebra case, we first consider resultants for dense differential polynomial systems. We suppose P0 to Pn are n plus 1 generic differential polynomials of order Si and degree Rr, and with coefficients Ui. Y1 to Yn are, as usual, the differential variables, ordinary differential variables. And we let D0 to be the set of all the coefficients of all the systems, all the specialized systems that has a common solution. We denote this set to be the coefficient set such that the specialized system has a common solution. And we take D to be the Coulton closure of this set. So by the generic differential intersection theorem, we know that exists this D is a codimension 1. So that by the differential characteristic set method, there always exists a unique irreducible differential polynomial R, such that the Coulton closure is equal to the general component of this unique differential polynomial. Okay.
So in algebra resultant, so it's resultant of two polynomials, right?
For univariate, the Sylvester resultant is for two polynomials in one variable.
Mm-hmm.
Yeah. And then maybe.
So you go with something else here. So what? There is. So could you explain the
for n plus 1.
But you talked before about the other result by McCall. Who?
Macaulay is for n plus 1 polynomials in n variables. It's a multivariate resultant. Yeah. And
It's n plus 1. N plus 1 n variable.
yeah. And okay, so this R is unique up to a constant in Q. And we define this R to be the differential resultant of the system. And for a specialized system like such system, the differential resultant can be obtained by evaluating the Ui by the coefficient of this specialized system into R. So yeah, this is the definition for the multivariate differential resultant. And for the n equal to 1, the case n equal to 1, it was already studied by Rich in his book, Differential Equations from the Algebraic Standpoint. Okay. So before I give the basic properties of the differential resultant, I first introduce the definition for sparse differential resultant.
So before we go, so is the question here given the P's find R or what? What's the question?
The question, you mean this definition?
Well, overall, so you introduced this. So how are you going to use it? So you're given this P's and find an R. Is that what the idea is?
Yeah, we want to find an element which gives a necessary and sufficient condition for the system to have a common zero. Can move on? Okay, so we also consider the sparse differential resultant for sparse differential polynomials. Since most differential polynomials in practice are sparse. And a sparse differential polynomial, here we roughly consider it as a differential polynomial with fixed differential monomials. Like this gives the difference between a dense differential polynomial and a sparse differential polynomial, both are of order 1 and degree 5. So this is the support of the dense differential polynomial of order 1 and degree 5. And this is the support of this sparse differential polynomial. Here, we didn't consider the degree of sparsity, so we regard this case as a special case of the sparse case. So that means because the sparse differential polynomial here is just defined as differential polynomials with fixed differential monomials. So this case is a special case of this case. And in the theory of algebraic sparse resultant, Laurent polynomials are considered. Here we consider Laurent differential polynomials. A Laurent differential monomial is a Laurent monomial in the differential variables and their derivatives. So it can have negative integers. Its exponents can be negative integers. And suppose A0 to AN are set of Laurent differential monomials in these n differential variables. And we denote Pi, this P0 to Pn are n plus 1 generic Laurent differential polynomials with support AI. And we let D0 to be the set of the coefficients of the specialized system which had a common non-polynomial solution. And we let D to be the cochain closure of D0 in this product space.
And what's the motivation behind the omitting polynomial solutions?
Because for the Laurent differential polynomials, the denominator them might be denominators. The
vanish.
Yeah, so
I
we
see.
want the it's whose derivatives all the solutions have non-zero derivatives. And we know D is an irreducible differential variety, but we don't know whether it is of codimension 1. So if D is of codimension 1, then there will exist a unique differential polynomial R such that the cochain closure is equal to the general component of this R. And we define, in this case, if it is of this case, we define R to be the sparse differential resultant of the system. And we say the sparse differential resultant exists for A0 to AN and denote it in this notation. So here comes a natural question. So under which conditions on the A0 to AN, on the suppose A0 to AN, the sparse differential resultant exists? So we first give the necessary and sufficient condition in terms of the differential transcendence degree. So this is naturally because it will require it is of codimension 1. And okay.
So you have some examples to show how this R could look like?
I will give later.
I'll give later.
Okay.
So also for the other case.
For the other case, you
Yes,
mean?
well, no sparsity, nothing. So
For the non-sparse case, the polynomial is too much terms, so I didn't list the terms, but
so would you say it's impractical?
impractical.
Impractical.
You might say this way. It might be very large polynomial. It depends on the order and the degree of the given system.
Do you know how to find it in some particular cases or in general?
Sorry?
In what cases do you know how to find it?
Yeah, we can find it. Just you mean we don't know whether it can be computed efficiently. Yeah, we know whether it exists. I will talk about it later. Yeah. So we give the condition based on linear algebraic techniques to show when the sparse differential resultant exists. So, we for
And is the reason to go into this rather than the general case that the general case is too impractical?
yeah, and also in the algebra case, for a very sparse system, their multivariate resultant might be 0. And in some problems, like the implicit Diffie problem, we want to eliminate some of the variables to get a non-zero algebraic relation between the other variables. If it is non-zero, if it is 0, they cannot provide any useful information. But for some sparse systems, if they, it can be the multivariate resultant is 0, but their sparse resultant is non-zero. So we can use it can provide more information for if we consider the structure of their sparse system. Yeah. Okay, so for MIK over MI0, it has such form, and it can be negative exponents here. And we introduce for each differential variable y1 to yn, we introduce n algebraic indeterminate x1 to xn, and to construct such a vector. For each Laurent differential monomial, we can construct such a vector, and for this system, we can construct a matrix. It's n plus 1 times n size matrix. And we proved that the resultant exists, the sparse resultant exists if and only if this matrix is of 4 rank. So this transfers the condition of, in terms of differential transcendence degree to a linear algebraic problem. And this is also equivalent to say there exists key 0 to key n such that this matrix is our rank n, it's 4 rank. So given n plus 1 set of Laurent differential monomials, we first can use this criterion to test whether the sparse differential resultant exists. Okay, so this is a simple example. For this example, A0, A1, A2 consist of these two, each one contains 2 differential monomials. And we can so use this criterion to show it is a Laurent differential essential system. This is equivalent to say the sparse differential resultant exists. And we can use the differential characteristic set method to compute the sparse differential resultant in this form. Yeah. Okay. So now we will give the basic conditions, basic properties for sparse differential resultant. So first, it gives necessary conditions and sufficient conditions in some sense for the existence of solutions. So to be precisely, if the system of differential equations have a solution, then their differential resultant vanishes. And if the differential resultant vanishes and its separate doesn't, then the system will definitely have a solution. And for sparse differential resultant, as we said before, it is related to non-polynomial solutions. So if a given system of sparse differential polynomials, they has a solution in has a non-polynomial solution, then their sparse differential resultant vanishes. And if the sparse differential resultant vanishes and its separate doesn't, then the given system will have a non-polynomial solution. Okay.
What kind of ordering are you putting on the differential variables?
Order?
Yeah, you talk about separance, right? Ranking, I mean.
Ranking. It's arbitrary ranking.
Arbitrary ranking.
Yeah. It's
so every separand is non-zero.
for this case, you just take one is enough. For this one, you just take one enough.
Right.
But in the definition, this is because there's just one polynomial. So with respect to any ranking, it can write in this form. And we also give the order and the degree bound for the sparse differential resultant. So let us recall the Jacobi number. So given a system of n differential polynomials in n variables, and we can write its order matrix. It's n plus n square matrix of size n, and each element is the order of gi with respect to yz. And the Jacobi number is the maximal diagonal sum. And the Jacobi bound conjecture claims the order of each component of G of differential dimension 0 is bounded by its Jacobi number. And for the order bound for the differential resultant, we saw it is differentially homogeneous in each coefficient set of polynomials, and the order in UI is equal to the sum of the orders of the other n plus n polynomials, differential polynomials. And for the sparse differential resultant, it is also differentially homogeneous, and its order is bounded by the Jacobi number of the other n polynomials, differential polynomials. And it also has Poisson-Type product formulas, like the Sylvester resultant can be written as these forms. And for the differential resultant, we also saw that it has Poisson-Type product formula. So here, f minus f0 is the derivative of this form. And after factorization, all these 8 tau are generic points of the zero-dimensional differential variety. This is irreducible differential variety. And the sparse differential resultant has a similar form, but we need additional conditions to show it can be right in this form to factorize 8 tau. So for this T0 points which lies on P1 to Pn.
Could you remind again, what was your definition of polynomial solutions?
Polynomial solutions is vector whose derivative doesn't vanish for up to any order.
Mm-hmm. And does your thing allow to check whether a system works? So are you saying that given a system of differential equations, you can say, you can detect whether it has non-polynomial solutions?
Yeah, if the sparse differential resultant doesn't vanish, it will definitely have no polynomial solutions. But if it is 0, yeah, we cannot tell exactly whether it has non-polynomial solutions. This is the same as in the algebra case. It is sufficient condition under some additional conditions.
What if you're looking at linear equations?
Linear, you mean for linear equations?
Linear differential equations.
Linear differential equation. I rather studied the linear sparse differential resultants, and you mean like this how it tells the solution, whether the solution exists? It's no special for linear and non-linear case. But yeah, for the computation, there will exist determinate forms to compute the sparse differential resultant. So for the linear case, it is easier to compute it. Yeah, but for the properties, it is not.
And do you know whether your thing will be if and only if in the linear case?
No.
No, so you have some examples showing that the linear
Yeah,
case.
because even for the linear case, the sparse differential resultant is not linear. So we still have the separate, yeah.
But it would be the case that the set of parameters for which you have, for which there's a solution, is Colchin constructible. So if you wanted to go further into this, you have your resultant, but then in principle, you could also compute differential polynomials, which would define the exceptional sets, and then the positive set inside of the exceptional set, and so on. I mean, it's a much harder problem to compute what that is, but it's at least in principle something that could be done.
Yeah, I think so. Yeah, I will talk about this later. And we also give the degree bounds for the sparse differential. All these properties are used to compute the sparse differential resultant. So this is the multivariate, the Macaulay resultant. The degree of the Macaulay resultant is the Biot number, and for the sparse resultant we have the BKK bound for the algebraic sparse resultant, and for the differential resultant we have such BKK type degree bound, but for sparse differential resultant, we don't know whether a BKK type bound exists. It is still a Biot type degree bound.
Could you explain the mixed volume thing?
Mixed volume? The definition is not that easier to describe. It's
Is it the Minkowski sum? Is it?
what?
Is it related to the Minkowski sum?
Yeah, definitely, yeah. This, yeah.
So I don't think that many people are familiar with
We
tasks.
have two blocks.
Two blocks.
It's a generalization of adding degrees,
No, but like if we assume that all supports are the same, then would it be just volume, right? Or like volume times something, times factorial.
Volume, if
If all supports are the same, maybe it would be just easy to describe for this special case. What does it mean?
for the mixed volumes, it's like compute the volumes, but there are some coefficients. I'm sorry, I cannot explain
Well, the whole thing is very complicated anyway.
Well, that's true. It's not a criticism, right?
No, it's just
But they have in Maple there is algorithms to compute the mixed volumes. Whenever you input the exponents of the support, they can compute the mixed volume as output in the Maple systems. And this example is for the for two univariate differential polynomials in one differential variable of degree 2. And the Biot type bound, of course, for the Biot type bound, it's easier to compute. It is just 81. But for the BKK type bond, for this, I can compute it by hand. For this example, it is 20.
But you're not suggesting to look for it with no, to look for a polynomial of degree 20 in these variables with undetermined coefficients, right?
Sorry, I cannot follow you.
So what's the reason to consider degree bounds? Just to get some idea how complicated it is?
Element the computational complexity of the to compute the sparse differential result.
But would you use the degree bound to actually find it or not?
Turn into linear algebra.
Well, but
You
that's
write
the
down the
question.
answer. You write down an answer.
Yeah, what's the size of the linear algebra question with?
Well, because it goes
with the-
exponentially with the bound.
Single-exponential. I will tell it later. So also we need the representation of the resultants. For the Sylvester resultant, we already know such a representation. And for the differential resultant, it can be written as a linear combination of the original system of polynomials up to the order f minus fi. Here, f is the sum of the orders of all the polynomials. And we have degree bound for the polynomial coefficients. And for the sparse differential resultant, we also have such degree bound for the linear combination. Here, Zi is the Jacobi number of the system. And this says if the differential resultant or the sparse differential resultant is non-zero, then we have one can be equal. One can be written to be the linear combination of pi and its derivatives up to the order zi. So, so if the sparse differential resultant or the differential resultant is non-zero, then we have a better bound for the Hilbert-Nash staircase problem. But when it is zero, yeah, we don't know.
Like, what's the relation between FIs and PIs?
Oh, sorry, this is FI.
Ah.
Yeah, this is FI.
Okay.
Sorry, this is specialized system. Yeah.
Beginning of the talk.
Yeah. Sorry.
So they're the same.
And this is all these properties are used to estimate the computational complexity of the sparse differential resultant. Yeah. Actually, this algorithm is based on linear algebraic computations by represent this polynomial as linear combinations of pi and its derivatives, and we have degree bound for the Gij. So we can search for. So this is, of course, this is the complexity at the worst case. And the algorithm is not efficient. We just use this algorithm to estimate the complexity. It is single-exponential.
Could you say again what linear system are you solving?
Sorry?
Could you explain the algorithm again?
The algorithm is just we know the order and degree bound for the sparse differential resultant.
Yeah, but
And we have this representation, and so we will just search for from order 0 to the order like Gi for the Jacobian. We search for such a polynomial. We use the undeterminate coefficient techniques.
I'm not getting it. So what's the condition? What exactly are you searching for?
We're searching for, we want to compute this polynomial.
It's just an answer in a huge number of linear terms. And then you just write down the conditions.
Yeah, we want, the algorithm is to compute the sparse differential resultant given P0 to Pn. We want to compute this
How do you
polynomial.
convert the condition for resultant into a question about linear system? I'm not sure.
Linear system?
This is it's an elimination problem, right? You want to eliminate variables y1, yn?
对
whatever.
yeah,
No,
yeah.
I'm really lost in the notation, so I'm not sure what you're talking about.
Okay.
All right, let's pass to the discussion.
So here, for this, we have coefficients for pi and y, the differential variables y1 to yn. And also for gi's, we have such variables, but for this is the sparse differential resultant is just involving the coefficients of the pi. This differential polynomial in the coefficients of the pi. So you eliminate y1 to yn to get this sparse differential resultant. So we have the degree bound for this polynomial and order bound, and also have the bound for this linear combination.
Yeah, but there could be many answers, right? How unique is this thing?
Unique?
Yeah.
Unique is guaranteed by the searching strategy. You search from order 0 to from order 0 to the degree bound, and no. You from the searching strategy, you search from order 0 and degree 1, and then keep the order invariant and how to say, to search a polynomial of degree +1, and then go on. If for this order there doesn't exist a polynomial up to the degree bound, then we put the order +1, and we then search for these degrees. So the degree bound, depends on the exact order of the sparse differential resultant. So the searching strategy guarantees the polynomial we find is the sparse differential resultant. Okay, so this is simple explanation, and as I said, it is not efficient. We want to find efficient algorithms, so here it comes a problem whether the sparse differential resultant or the differential resultant have matrix representations.
What is this? IJ2?
IJ?
IJ2.
You mean this?
No,
In the degree, in big O. M
exponent.
m to the power.
Sorry, maybe.
IJ2.
Yeah.
Oh, it's square.
Actually,
Oh,
it is. Is it that square?
Sure.
Oh.
Sorry.
It's a good thing.
Sorry.
The mysterious IJ2.
Yeah. Sorry. And we want to find a matrix representation. If the sparse differential result or the differential result can be computed as the quotient of two determinants, then we can have efficient algorithms to compute it. And now there are very limited results up to now. For differential resultant, resultant of two univariate differential polynomials of order 1, they give Zhang et al. Give the matrix representation. And for the linear case, rather give the determinant forms for some special cases. Okay, so this is for the differential case. For the difference.
May I ask about this? So when you say linear case, you mean the original polynomials are linear?
Yeah.
I see. Thank you.
Okay, so for the difference case, I just use this one slide to show the difference between sparse difference resultant and the differential case. So for the definition of the sparse difference resultant, it becomes more complicated because the difference characteristic set method is more complicated. In particular, if this idea is our codimension is a reflexive prime difference idea of codimension 1, there might be other polynomials in the characteristic set, and these polynomials may be different depending on different rankings. This is not in the not as in the differential case, but we proved that the first polynomial, the first irreducible difference polynomial will be unique up to any order. And we define this R to be the sparse difference resultant. But we conjecture here M should be equal to 0 for this particular definition for sparse difference resultant, but we cannot prove up to now. And for the essential criterion, that means the criterion for the existence of sparse difference resultant or sparse differential resultant. Here, for the difference case, it is much simpler than the differential case. Because the Leibniz rule will destroy the structure of the differential monomials, but for the transforming operator will keep the difference monomial, just to lift the order for each variable to +1. And for the matrix formula, for the difference case, we have matrix formula for difference resultant. Yeah, for the differential case, we still don't have. And for the difference case, we consider non-zero solutions because the denominators of the Laurent difference polynomials may have denominators. The difference monomials may exist in the denominators of the Laurent difference polynomials, so we require the solution to be non-zero ones. That means for each element, its transforms is not 0.
Where are you looking for the solutions in the difference case?
What?
What kind of difference ring are you using to find solutions
It's
in the difference case?
just a difference extension field. It is like in the common sense is uniform. Not uniform. It's universal. To say the concept.
Domain.
Yeah.
In the field, but she's saying the field, right?
Yeah, I said a field like in Weber's the Michael's things is you can consider the differential variety as a functor. As a functor, and then any differential field, if it has a solution in any differential field, it works here.
Okay, so
Difference fields.
Inverse fields.
Inverse fields.
Inverse difference
Oh, of
fields
course.
is-
Yeah, inversive. Yeah.
Do you get a different answer if you look in rings of sequences?
No, we don't know.
What is M? M what?
M here is a difference monomial. So for you mean the homogeneity property?
Big M.
What?
Matrix formula. What is this? What is this M?
Determinant big M.
There are several different big M's. I think Alexei refers to the third row. Matrix,
Third row.
matrix formula.
Sorry, what I
Third row.
Determinant M, determinant M.
third row this?
Yes. So what's M?
M.
Oh, M is M is a matrix constructed from the coefficients of the differential polynomials, and M0 is a submatrix of M. It is based on the subdivision method, like in the algebra constructing the determinate forms for algebraic sparse resultant is, I didn't write it down here. And for the degree, the degree of the difference resultant is exact the BKK number. Here for the difference case is a bound. And for the outer bound, they are the same. So, okay, so this is the basic things for sparse differential and difference resultant. And there are other properties not related to how to compute it, so I didn't talk it here. Okay, like the differential toric variety and the difference toric variety, they are related to the sparse differential difference resultant. Okay, so it has example. This example it gives the difference. The three differential polynomials or difference polynomial have the same support, but they are sparse differential resultant or difference resultant is not the same, and the degree is also not the same. Okay, so here is the summary. So we discussed the theory of sparse differential and difference resultants, and so the computational complexity of it is single exponential. And for further problems, of course, we want to find matrix representations for the sparse differential resultants. And in the definition of sparse difference resultant, we want to show m is equal to 0. So.
Have you programmed the algorithm?
No, it is just a theoretical one.
Do you know the constants in the big O's?
The constants in Wiggles?
Yes, in big O. You have big O or something. Is it like billion? Is it billion to billion? Or what is it like? How big are the constants?
The constants?
Yes, so in your, could you show the complexity bound again? Yes.
Oh, you mean this?
Yeah, so what kind of useful information does this give if you don't know the constants?
No, there is no constant here. Just write it down. This seems simpler, but we have exact number for this.
You have actually exact numbers there?
Yeah, we have
How do they look like?
It's also single exponential. Just when you write it down, it's a large number.
A large number.
Yeah, but it's also single exponential. A single.
What do you mean by single exponential for a number?
Like this. Maybe this is not O, but just some special numbers.
But what is that number?
The numbers. Like this case, it has some.
Is it less than a million?
What?
Less than a million?
No.
It's more than a million.
No, it's.
So it's a million.
No, sorry. Can I show it later to you?
It's not talking about constant or proportionality.
What?
You should, but.
I can write down it later, but in the slides we just want it to look small. We write it with a small space, but we do have the exact number for the complexity. Okay, so okay, I should finish it. So also for the for the partial differential polynomials, how to develop a resultant theory. We don't know how to do that. Yeah, we don't know. Okay, so this is what I want to say today. Thank you.
We have time for maybe one short question.
I have a general question. So let's just look at even the algebraic case,
Okay.
even for two polynomials.
Okay.
So we can compute the resultant from a determinant.
Yeah.
That's not very hard, of course, right?
Yeah.
But solving the two equations, actually finding a common solution may be very hard. Very harder, is that correct?
Yeah, but for the algebra case, yeah, if you
I mean, if you use from the basis to try to find a solution.
So-
are you asking what to do with the resultant next?
No,
or once you
no,
compute
I'm
it?
how to do polynomial
I'm actually trying to
solving,
compare
right?
the complexity of computing
How to
resultant
compute the
and the
integral
complexity
number.
of trying to solve a system.
Oh, okay.
Well,
Yeah.
she's not solving the system, she's
I
checking
know,
whether
I know.
there is a solution.
That's why I said
different.
I'm asking for a general question.
Oh, even if you
Ah.
have a single equation, how do you solve it?
Yeah, it is hard to give the exact solution.
Solving it.
Yeah, y prime is equal to y. How do you
Well,
solve
but
it?
then what's the point
how
of
do you
finding,
solve
knowing that there is a solution and not knowing it?
Since the
this?
19th
There
century.
are reasons to
No, I mean,
And it is,
there's a point to don't know if there is no solution.
Okay.
Because then if there is no, you don't lose your time on trying to find it, right?
Yeah.
So that's the point.
Well, but no solution where?
Well, they have
It's just
theories.
anywhere, so
They have theories.
so don't look.
All right.
That's thanks for your reading.
Do the slides abort?